turn it on, make sure it works. I can trim the beginning after. Okay, excellent. I think we are live.
Okay, shall I go ahead?
Oh, thank you, Ian. And we have a pleasure to welcome Ian to virtually, Ian Affleck, to our workshop, which is unfortunately virtual, but still we are very happy you can join us. And I have not been very successful with introductions, but my hope is that at least in the case of Ian, no introductions are needed, indeed, even for this diverse audience. So with that, Ian, please feel free to take it away. And we're looking forward to.
Yeah. By the way, my name's actually pronounced Ian, not Ian.
Okay, sorry.
Okay, so I worked on this Myrana Hubbard model for quite a few years with quite a few collaborators. So Armin Ramani was a postdoc of mine. He's now a professor at Western Washington University. Marcel Franz is a professor at UBC. Dima Pakulin was a postdoc at UBC. He's now works at Microsoft Station Q. Tarun Tumaru is my master's student. He's now doing a PhD with Marcel. Kyle Weimer was my PhD student. And Xiaoyu Zhu was a visitor from China for a year. So here's the outline of the talk. First of all, I want to give the motivation and the model. Then I want to talk about the one-dimensional case, the square lattice case, including some numerical work on ladders, triangular lattice case, and then conclusions. Motivation and model. So a macroscopic number of Myrana modes are predicted to occur if a layer of ordinary superconductor is placed on a strong topological insulator in the transverse magnetic field. So there's a diagram illustrating that. So every vortex has a Myrana in its core. Myrana fermions are a candidate for qubits. This has led to great interest in them. It's been the main focus of research at Microsoft Station Q, where Charlie Marcus at the Niels Bohr Institute is one of the leading experimentalists working in this field. Various experimentalists have claimed to see Myrana fermions, but this has remained controversial. Interaction effects involving Myrana fermions have not been studied experimentally. At least two experimental groups are interested in studying them to test our theoretical predictions. So Myrana mode is localized near the center of each superconducting vortex. And Myrana modes can tunnel between vortices and interact with each other with short-range interactions that go like exponential of minus r over xc, where xc is the coherence length for the superconductor. Tunneling amplitude can be taken to zero if a gate voltage chemical potential of the topological superconductor is tuned to a special value. So that means we can effectively tune to very strong coupling by changing the gate voltage. That motivates studying this model with interactions. So we studied the simplest possible version of this model with the shortest possible range interactions. And we call this the Myrana Hubbard model. So it has a hopping amplitude T, it has interactions G, and we let G over T be a Wiener sign because it's not quite clear to us whether the interactions could be effectively attractive or repulsive, given that we're dealing with a superconductor. So far we've studied the one-dimensional case, the two-dimensional square ladder, square lattice ladders, and triangular lattice ladders. So here's the one-dimensional model. So we have gammas are Myrana fermions, they're Hermitian. So gamma j dagger equals gamma j, and the anti-commutators are gamma j, gamma k is 2 delta jk. And here's the Hamiltonian. We have the shortest range hopping, nearest neighbor hopping, and we have interactions. Because gamma j squared is 1, we have to have interactions on 4 lattice sites. So the simplest possible interactions are on 4 neighboring sites: gamma j plus 1, gamma j plus 2, gamma j plus 3. So there are no conserved particle number in this model.
Ian, sorry. Ian,
yeah.
We
yeah.
had big delay of this current slide. It wasn't showing for a while. So maybe
I'm sorry. Yeah, I have very bad internet on this island. That's part of the problem. You can see it now. Yeah.
we can see it now.
Go over it again. Yeah. Okay. So here's the Hamiltonian. So nearest neighbor hopping, and interactions have to be in 4 lattice sites because gamma j squared is 1. So there's no conserved particle number in this model, but they're important discrete symmetries. And this model we've studied extensively by field theory and also by density matrix normalization group. Here's the next slide. Can you see it?
Not yet.
Not yet. Okay. I'll wait a minute.
Video to just see whether that works. We see the slide now.
Yeah, I think it's just some kind of delay. I think it's the bad internet I have here.
Maybe
okay.
blank the video.
Yeah, your video.
Sorry, what can I do with it? I want to be able to see it myself, of course.
Yeah, but maybe we will be able to see the slides better in that case.
If I do what?
You just turn off your video. If you turn off your camera, so we won't be able
turn off my video.
Yeah.
Okay, stop video. Okay.
So let's try now. If you.
Okay. So I stopped the video. Okay. All right.
Let's try
okay.
that.
Okay, good. So the Majorana's like, in a sense, to pair up to form complex Dirac fermions. And we've seen lots of numerical evidence of that. So we can define a regular complex fermion Cj by combining 2 Majorana fermions. So for example, we can form Cj to be gamma 2j plus I, gamma 2j plus 1 over 2. And now we can calculate I gamma 2j plus 1, and it can be easily seen to be twice C dagger j, Cj minus 1. So if we look at the interactions, half of the interactions become quite trivial. They become minus g sum over j, twice C dagger j, Cj minus 1, twice C dagger j plus 1, Cj plus 1 minus 1. The other interactions become very complicated, and I'll show them to you in a minute. So notice that g bigger than 0 is actually attractive, and g less than 0 is repulsive because of this I squared factor. So there's no conserved charge. So the mean field density is determined by interactions, and it's cannot be controlled. So there are 2 mean field ground states for positive g corresponding to attractive interactions. And I've sketched them here. So we can combine a pair of Majoranas to form a Dirac fermion. And it turns out that these Dirac fermion states want to be empty because of the sign of the hopping term. And there are 2 ways of pairing up Majoranas. We can either combine them this way or that way. So that gives us two states. Okay, next slide. Can you see it now? Let me know when you can see the next slide.
Yeah, we see it now.
Okay, good. So we can write the full Hamiltonian in the complex fermion basis. And we define Pj hat to be twice C dagger j, Cj minus 1. So here's the Hamiltonian. So the first 2 terms are kind of trivial. And the next terms, well, t times Pj is simple, and g times minus Pj plus 1 is simple. But then we have rather complicated terms. So we have a hopping term, which also involves not only hopping, but also nearest neighbor pairing term. And now we have rather complicated interaction terms that involve 3 sites, actually. So C dagger j minus Cj, Pj plus 1, C dagger j plus 2 plus Cj plus 2. So if we keep only the first t term and the first g term, this is mean field theory. And remarkably, this turns out to be qualitatively correct at large enough g, as we will see. Okay, can you see the next slide yet?
Yes, we see it.
Good. Okay. So for negative g, which is repulsive interactions, there are actually 4 mean field states, because now we form the Dirac fermions. They want to basically go into a charge density wave. So empty filled, and so they're all together. There are 4 sites because we can pair up Majoranas 2 ways to form Dirac fermions, and then we can do empty field, two different ways. So we get 4 mean field states. And remarkably, we've confirmed that these are the ground states at large enough negative G. This is a charge density wave. So we verified all of this using DMRG. Okay, next slide. Can you see it?
Yes, we can see it.
Good. Okay. So a non-interacting model we can solve quite easily. So we can just Fourier transform. Notice, however, that gamma k is not Hermitian, even though gamma j is. But gamma minus k is gamma k dagger. So we can actually restrict ourselves. So we can diagonalize and restrict ourselves to positive k. And the Hamiltonian becomes 2t times sum over k from 0 to pi of gamma k dagger gamma k times sine k. So we don't have any holes, we only have particles. So the ground state simply has all states empty. And we only have particle excitations, not holes. And this is a signature of Majorana fermion. So I'll show you the relativistic version of this model momentarily. So the low energy excitations have linear dispersion, as we can see from this curve. Okay, can you see the next slide?
Yes.
Good. Okay, so we can write gamma j as twice gamma right plus minus 1 to the j twice gamma left. So gamma right is just the excitations near k equals 0, and gamma left are the excitations near k equals pi. And now we can Hamiltonian, and this is a relativistic Majorana Hamiltonian involving gamma right and gamma left. And gamma right and gamma left are Hermitian. And the velocity v ends up being 4t. So these operators have normalization group scaling dimension 1/2, so that h has dimension 1. And the lowest dimension continuum interaction is this. So it's minus 256g integral dx gamma right, gamma left, dx gamma left. So we have to have these derivatives here because gamma right squared is a constant. And this is dimension 4. So it's highly irrelevant at weak coupling. But it turns out that if the interactions get strong enough, eventually this will become relevant. So we expect to get free Majorana dispersion, at least for small enough g. Okay, next slide. Tell me when you can see it.
Yeah,
Yes, could I also ask where the 256 comes from?
Yeah, that just comes from just I think this the transformation from the lattice model to the continuum model. This which factor comes in? Good question. Yeah, I think there are a lot of factors of 2 that come in.
Now it seems to work pretty well. So when you try to go to the next slide, it just takes maybe a second.
Okay, very good. Great.
So I will tell you if it gets longer, okay?
Yeah. Okay, so we studied phase transitions using density matrix normalization group. And remarkably, the transition for positive G occurs at G near 256. And the transition for negative G occurs at G near -3. So this makes the numerics very challenging at large positive G. But Armin Romani was able to do the numerics eventually. So the correlation length is infinity for G between 0 and 256. It only comes down to perhaps a few hundred at G of infinity. So the nature of the second order phase transition for G of 256 is interesting. So the critical line with G less than 256 corresponds to the one-dimensional quantumizing model, which you can map from spins to Majorana fermions. And this model has a critical point at h equals 1. And the symmetry that keeps the model critical is translation by one site, which takes gamma right to minus gamma right. And this forbids the mass term m gamma right, gamma left. So the corresponding symmetry in the Ising model is called Kramers-Wanier duality. And this is a symmetry which takes h-1 to minus h-1 for h near 1. So it switches the broken and unbroken symmetry phases. So the Ising transition becomes first order if we insert a high enough density of randomly located vacancies. This transition by using spin ones instead of spin a halves, inserting an SZ squared term which favors SZ equals 0. So this is the famous Hamiltonian for studying the tricritical Ising point. So this is spin 1 now, and we have an SZ squared term, and we have I've taken the linear term now to be the x direction, not the z direction. So in this curve, the solid line is a second order transition, and the dashed line is a first order transition, and the star marks the transition from second to first order. This point is called the tricritical Ising model. This model is a supersymmetric conformal field theory. So for G slightly bigger than 256, we predict fermions and bosons of the same mass. And in fact, we're currently studying this now, and we hope to have a paper on this topic soon. So it turns out that the only relevant operator is preserved supersymmetry, but supersymmetry is spontaneously in the Yang phase, but not in the larger G phase. But the larger G phase has a broken translation symmetry, but does not have broken supersymmetry. So this is the full phase diagram that we found for the one-dimensional case. So so there's a range near 0 where G over T is near 0, where we have the Ising phase. This extends from negative G to positive G. We have the tricritical Ising point, and then we have a gapped twofold degenerate supersymmetric region for larger G. For negative G, we have a couple of rather remarkable transitions. So there's an Ising, there's a phase here which is Ising plus Luttinger liquid, which I'll explain in a minute. And this transition is actually a Lifshitz transition. So it's not a field theory transition. It actually involves a cubic dispersion relation. And then there's a generalized commensurate incommensurate transition that occurs here. So this is about minus 0.3, and this is about minus 3. And then for large enough negative G, we get this gapped fourfold degenerate state that I showed you in a previous diagram. And for large enough positive G, we get the gapped twofold degenerate state. So the mean field theory turns out to be correct. And if we go to infinite G, so T is 0, then G over T are equivalent. So we have equivalent phases here. And the low-lying excited doublet has an energy proportional to T for small t. There's also a remarkable intermediate phase for G less than 0, which is repulsive interactions. This can be understood from interactions modifying the dispersion relation for the free Majorana fermions. So second neighbor hopping is not allowed by symmetry, but the symmetry is time reversal. It takes I to minus I and gamma J minus 1 to gamma J. But if third neighbor hopping is allowed, this gets generated by interactions. So if we modify the dispersion relation to include a third neighbor hopping, we'll get an epsilon of 2t sine k plus 2t3 sine 3k. And this is a curve of what the dispersion relation looks like. So for T3 equals 0, it's the curve I showed you before. For T3 large enough, we actually we have a more interesting phase diagram. So it goes down, and then it goes up, and it goes down and goes up again. And we actually get Dirac fermions at the point K0 and pi minus K0, but Majorana fermions at 0 and pi. And at the point T3 equals T over 3, we actually get a cubic dispersion relation. And we think that the critical point first critical point that occurs for negative G corresponds to this cubic dispersion relation. So for T3 bigger than T over 3, we have a low energy theory that has both relativistic Majorana fermions and also complex fermions. So complex fermions near K0, pi minus K0, and Majorana fermions near 0 and pi. So we can write a corresponding field theory, interaction terms. And we have both the standard Luttinger liquid interaction term, psi right dagger, psi right, psi left dagger, psi left. And we also have a term that couples the Majorana fermions to the complex fermions. So the first term will determine a Luttinger liquid parameter. The second term is irrelevant, it turns out, for repulsive interactions for G less than 0. There's also a term that alternates with a wave vector determined by K0. This is psi right dagger dx, psi right dagger, psi left dagger cx dx psi left, and this has a phase e to the I 4K0 minus pi times x, where K0 varies as we change the interaction rate. This is irrelevant unless the repulsive interactions are very strong. So if K is less than 1/4, and this oscillates, unless K0 is pi over 4. So this transition into the C equals 3/2 phase at G equals minus 0.3 is a Lifshitz transition, not relativistic dispersion, cubic dispersion relation. Transition out of the C equals 3/2 phase into the strong coupling broken symmetry phase occurs at G equals minus 3. And it occurs because K goes to 1/4 and K0 goes to pi over 4 simultaneously. So we simultaneously find that this interaction suddenly becomes relevant because it stops oscillating and becomes marginal at the same value of G. This is actually a bit reminiscent of what happens in some other types of field theories that have been studied previously. So we can calculate both the latent liquid parameter and K0 using DMRG. We get the finite size spectrum conclusion. Okay, so that's all I want to say about the one-dimensional case. Now I'm going to move on to the two-dimensional square lattice case. So here's the Hamiltonian for the square lattice. It turns out that we actually have an alternating hopping term. So the horizontal hopping term alternates in sign, and this is determined by the requirement that we have one flux quantum per plaquette. So this is fixed by determining this Majorana model from the superconducting layer on the topological insulator. And the interactions we take to be the shortest possible range, so they're on a square plaquette in this case. And then we could include second neighbor hopping, but that breaks symmetries. And I'll discuss the effects of that later in some of these slides. So again, G positive is attractive interactions and G negative is repulsive because of turning over to Dirac fermions. So the T2, yes.
Interrupt just a bit. So what are the symmetries of these models? Maybe you said it.
Okay, good question. So they're quite limited symmetries. So we have symmetry of translation by one site. In the square lattice case, we also have symmetry of translation by pi over 2. So those are basically the only symmetries. And we have time reversal if T2 is 0. So I think those are the only symmetries. We have translation by one site. We have rotation by pi over 2. We have time reversal.
Okay, so just lattice symmetries and time reversal. Basically.
Yeah, but remarkable symmetries actually are generated in the field theory, as I will explain.
I see. So there are emergent symmetries.
Yes, exactly.
Okay.
I have a question about the sign of the hopping. Now, is that required, or is that something you chose based on some microscopic consideration?
No, we can just, in fact, I think if we just change the sign of the hopping, we can just, I think it doesn't change any of the physics, actually. So it's just convenient to choose the hopping to be positive.
I meant the -1 to the end.
Oh, yeah, this is determined by the requirement that we have one flux quantum per plaquette. So,
but I guess the model is defined, well defined, even if you didn't have that -1.
Yes, but if it comes from this from the superconductor, then this sign has to be here. In fact, this observation was made a number of years ago by some previous authors.
I see.
I actually have a follow-up question. So perhaps I apologize if you said this already, but
yep.
What is the motivation for studying these models? What are the
Okay, the motivation is that you can actually realize them experimentally. So if you put a superconducting layer on top of a topological insulator, and then you apply a magnetic field, it's predicted you have a Majorana mode at the center of every vortex core. And we can expect that these Majorana modes can hop from core to core, and that they also have interactions. So the most natural theory would actually be two-dimensional, because we're looking at a two-dimensional superconductor. So the one-dimensional model is a bit unrealistic, but I guess if we formed a very thin layer of superconductor on top of a topological insulator, we could perhaps realize a one-dimensional model.
I
Or the
see.
two-dimensional model. And in fact, the most natural two-dimensional model would be triangular because vortices are normally triangular. But there are certain superconductors which actually have a square vortex lattice.
I see.
But-
So,
but-
so a vortex lattice gets formed, and they have Majorana fermions there, and you want to study the phases of that theory.
Exactly, yes.
Okay, thank you.
Yep. Okay, so the T2 term breaks time reversal and parity symmetry and changes the phase diagram significantly, as I will discuss. So the phases are characterized by spontaneously broken symmetries. So what are the symmetries of the Hamiltonian which might get broken? So translation by one site in the X or Y direction, pi/2 rotation, or if T2 is 0, only time reversal. Also, there's a parity or spatial reflection symmetry. I should have mentioned there's also a parity or spatial reflection. Even if T2 is non-zero, there's a PT symmetry, which is a combination of parity and time reversal. In addition, there are emergent symmetries in the low energy field theory, which I will discuss. So these pairing phases also break rotational symmetry. And in fact, we're predicting that we get Majoranas pairing up to form Dirac fermions. So if G is positive, then these states, the mean field theory, these states are empty. But now we actually get 4 states because we can pair up Majoranas this way, or we can rotate it and pair them up horizontally instead of vertically. So we get 4 different states in the mean field theory. If G is negative, then we get these particle hole type states. Now we actually get 8 states because if we pair up the Majoranas this way, then we can form particle hole, or hole, particle. Or then we can also rotate. So altogether we get 8 in this case. And I should mention that the two-dimensional case we have not studied numerically, but we have studied ladders, 2-leg ladders and 4-leg ladders, which I'll get to momentarily. So these pairing phases also break rotational symmetry and parity symmetry for T2 equals 0, and time reversal. So time reversal takes gamma mn to -1 to the m plus n gamma mn, I to minus I. And this is broken by the second neighbor hopping term. Now let me talk about the field theory normalization group approach and the nature of the critical points. So for the non-interacting case, we can find the exact dispersion relation. So if T2 is included, T2 is 0, we get just plus or minus square root of 4t sine kx squared plus 4t sine ky squared. So we get a gapless dispersion relation. If T2 is included, we get a gap. And if T2 is small enough, we actually get a Lorentz invariant dispersion relation. It looks a little bit like graphene, but we have Majorana modes instead of Dirac fermions. Now we have a small mass, which is determined by T2. So we get 2 valleys. So again, we can restrict ourselves to kx positive from the Fourier transforming, and the fact that the gammas are in position space are real, or Hermitian. So we get 2 points in K space which have low energy excitations, one at 0, 0, and one at pi 0. So low energy field theory has 2 species of 2-component Majorana fermions. These can be combined because we have 2 different points in K space because of the sign alternation. So we have 2-component Majorana fermions. These can be combined into a single species of Dirac fermion, which is relativistic. So ignoring higher derivative terms, the Lagrange density, including the is Lorentz invariant. So we have so written in terms of these Dirac fermions. So we have the usual Dirac fermion Hamiltonian. The mass term will be present if T2 is non-zero. We also have the interaction term psi bar psi squared. The gamma u are the usual 2-dimensional gamma matrices. And I've set the velocity to 1 for convenience. And psi bar is psi dagger gamma 0. So there are 2 components from inequivalent even and odd rows, as I mentioned. So in addition to Lorentz invariance, there's an emergent U1 symmetry, remarkably. So both Lorentz invariance and U1 symmetry have emerged. So interactions are irrelevant in normalization group sense if bare G is small enough. So it normalizes to 0. And this is true because I guess in 2 + 1 dimension psi has dimension 1, and this has dimension 4, and the marginal case would be 3. So right interactions in this way. So for G positive, this is an attractive pairing interaction. We expect to get a transition to a superfluid phase for strong enough positive G, corresponding to ferromagnetic pairing phase. There's also a higher dimensional term which breaks U1 symmetry. We'll go back to that. So for T2 0, the fermions are massless in the G less than G critical phase. At the superfluid transition, we get a massless Goldstone boson, as well as massless fermions. So this transition is supersymmetric because we have equivalent massless fermions and bosons at the supersymmetric point. And indeed, this Dirac fermion model has been studied previously and has been known to be supersymmetric. But what's unique here is that this appears from the Majorana fermions. A non-zero T2 gives fermions a mass, and this destroys the supersymmetry. Now we expect the superfluid transition to be in the usual UN breaking 2 + 1 dimensional universality class, or I guess it's sometimes known as Wilson-Fisher.
So I have a quick question.
Yep. Go ahead.
The non-zero T2 gives fermions a mass. Now T2 is a parameter in the UV Hamiltonian.
Yes.
What's special about T = 0?
Well, if you look at the dispersion relation, okay, if T2 is 0, we have a gapless dispersion relation. And indeed, the relevant. So we remain in this gapless dispersion relation. So the fermions are gapless if T2 is 0. But if T2 is non-zero, we get a gap. It becomes a massive.
This is non-interacting model, right?
This is non-interacting, but the interactions are irrelevant if they're weak enough. So we were normalized to this phase if G is small enough.
But then you would expect really that this point T = 0, where you have gapless excitations, that it be shifted. I mean, even though you have irrelevant terms, they will renormalize the point.
Yeah, we'll normalize the parameters, but we expect that if T2 is non-zero, which breaks a symmetry. So if T2 is 0, there's a symmetry that forbids T2 being generated. But if T2 is...
So that's what I mean. So T2 = 0 is enhances the symmetry. Which symmetry does it break?
It's time reversal symmetry. So T2 breaks time reversal symmetry.
Okay.
So
okay.
Yeah.
Thank you. Yeah. So it will remain there.
Yeah.
Excuse me, I have a question. Hello?
Yep.
Yeah, I have a
Yep.
question. I'm a bit behind. If you go back to the original model in 2D, if you did not have this pi flux, right, you had this sign structure, then I suppose, so is it correct that all the emergent Lorentz symmetry which you observe would not be there?
Actually, that's a good question. I think we haven't studied that carefully. That's a good question. I suspect much of the model would look the same, but there would be some differences, I'm sure, because of this -1 to the n. In particular, the fact that we get two-component Dirac fermion as a result of having this sign alternation.
Could
So
you,
it kind of cuts in half the Billman zone.
Could you, so I'm sorry to insist, but would you also have the second statement that you say that correlations are not important? What the scaling dimensions is, so they're not important, they're small enough. Would that also hold if you did not have this sign structure?
Yeah, we haven't studied that carefully. That's a good question. Yeah, I'm not entirely sure.
Okay, thank you.
I suspect things to be rather similar, but we might not have this Lorentz invariance.
Thank you.
And there's also UN breaking term. And I studied this with Kyle Weimer, my PhD student. So the UN breaking term is higher dimension. It's psi1 dx psi1, psi2 dx psi2, minus psi1 dy psi1, psi2 dy psi2. So this is even a higher dimension. This would be dimension 6, because the fermions have dimension 1 and we have 2 derivatives. And we studied this using the epsilon expansion and showed that this interaction is irrelevant. So we think we can ignore this interaction, at least using the epsilon expansion. Another interesting feature of this model is that this model actually evades the Nielsen-Ninomiya theorem. And we only have one channel of Lorentz invariant fermions in the low dimensional, in the lattice model. And yet we get this Dirac fermion. And this is a result of having U1 symmetry broken and having Majorana fermions, not Dirac fermions. Okay, so now let me discuss results on ladders. So we've studied 2-leg and 4-leg ladders. So with square lattice geometry, by a combination of analytic and DMRG methods. So in the 2-leg case, as we can see by defining complex fermions. So on the 2 legs, we can combine the fermion on each leg. So gamma M0, gamma M1. So we can define a complex fermion this way. The horizontal hopping term becomes CM dagger CM plus 1 minus Hermitian conjugate. And the vertical hopping term becomes minus 1 to the M CM dagger CM. So we don't have any breaking of U1 symmetry in this case. So we can actually rewrite this in terms of spins. And the corresponding Hamiltonian becomes T sigma mx, sigma m plus 1x plus sigma my, sigma m plus 1y, plus 2g sigma zm, sigma zm plus 1. So if G is weak enough, we're in a gapless phase. But if G is not phase, and we can show that I gamma M0, gamma M1 corresponds to minus 1 to the M sigma Zm. So we see that any ferromagnetic order occurs for G bigger than 1/2. This corresponds precisely to the mean field ground state that we predicted. So the exact symmetry breaking in the lattice in the spin model confirms the mean field prediction that we made. And the ferromagnetic order occurs for G less than minus 1/2. This corresponds to this mean field ground state, which is also what we predicted. Okay, so that's a confirmation of our mean field based on an exact mapping for the 2-leg ladder into a spin chain. So for the 4-leg case, things get more complicated. The model is not analytically solvable except at infinite coupling. So we analyzed it with DMRG. So to analyze the infinite coupling limit, we define complex fermions. So now we have four legs. So we define a complex fermion CM1, which is gamma M0 plus I gamma M1 over 2. Then a second complex fermion, which is gamma M2 plus I gamma M3 over 2. So we've numbered the 4 legs 0, 1, 2, 3. So it can be seen that the interaction term preserves fermion parity in each rung, unlike the horizontal hopping term.
Sorry, Ian, could I ask a question? What do you mean by 4-leg case? What?
It's just a 4-leg ladder. So we just have 4 legs, and we study this numerically and also analytically to some extent. So we just have a 4-leg square lattice. So do you want me to draw a picture? It's just 4 legs in a vertical, forming a square lattice.
So
just
a square lattice?
It's a square lattice, but we only have 4. It's infinite in the x direction. It only has 4 legs in the y direction.
Oh, it's a 4 sides. Okay, I see.
Yeah. Okay, good. Thanks for the question. Okay. So at strong coupling, we can restrict ourselves to only 2 states with fixed fermion parity in each rung. And we can map these states into the XY model with the Hamiltonian, so only including interactions, but this is the Hamiltonian. So this is the gapless XY or in this case, actually XZ model. So for only G and no T, we predict a gapless phase. So unlike the 2-leg case, this model is gapless with no broken symmetry, except for fermion parity. Adding a small hopping term produces a gap. So if we add a hopping term in the y direction, for small t over g, we can ignore horizontal hopping since it changes the fermion parity in each run. This can be shown to increase the energy by an amount of order g. So on the other hand, vertical hopping just gives a perturbation, a t term, which is kind of like a magnetic field. So, depending on which way we pair up the fermions, we either get this Hamiltonian or this Hamiltonian, which are actually equivalent. So the vertical hopping just gives a perturbation. And so for even fermion parity, we get this, and for odd fermion parity, we get this. So this leads to a gap states with the spins ordering in the z or the x direction for even or odd fermion parity for g bigger than 0. So for even fermion parity, I gamma 0, gamma m1, and I gamma 2, gamma m3 goes to sigma zm. So ferromagnetic order corresponds to Majoranas pairing up to form Dirac fermions. On the other hand, for odd fermion parity, gamma m1, gamma m2, and gamma m3, gamma m0 go to sigma xm. So we get the other mean field state. So again, this actually confirms the mean field predictions, at least a strong coupling based on using this mapping to Majoranas, which only holds for very strong coupling. So for positive G, we only find one transition. So we can map it into complex fermions, ignore interactions, and we get one gapped complex fermion, one gapless complex fermion. With small g, we may integrate out the gap mode. Then we find the UN breaking interactions are irrelevant, and the UN preserving interactions are a standard spinless fermion liquid form corresponding to an Umklapp term. So we thus predict a Kosterlitz-Salvas transition into a gap phase at sufficiently strong G. This agrees well with DMRG results. So the 2D limit, we expect this transition to become supersymmetric, but in the ladder model, we don't see supersymmetry. So there are also 3 additional transitions in the 4-leg ladder for negative G with stable phases with central charges -3/2, 2, and 1, which we haven't fully understood. So open questions here. And finally, in the remaining few minutes, let me go on to the triangular lattice case. So this I studied with Tarun Tumaru and also Alberto Nocera. They did some numerics on this. So this is the triangular lattice case. So again, the hopping terms can be positive or negative. And again, we have a requirement of 1 flux quantum per plaquette. And the signs are indicated by these arrows here. And now the interactions are more complicated. So again, we take the shortest possible range interactions. But now we actually have 3 different plaquettes on which we can form the interactions, which I've drawn here. And now if we solve the non-interacting case, now we find that even with only nearest neighbor hopping, which is the only thing we studied, we have a gap. So there's 2 phases and there's a gap separating them. Now we have 3 types of plaquettes. So now the mean field state only minimizes the energy in 1/6 of the plaquettes. So if we combined pairs of Majoranas to form Dirac fermions, this would only lower the energy in 1/6 of the plaquettes. So we predict in this case that we don't get broken symmetry. So mean field theory doesn't predict broken symmetry in this case. Doesn't predict the Majoranas pairing up to form Dirac fermions. And DMRG results in the 4-leg ladder do not find broken symmetries, even at strong coupling. This is consistent with the mean field theory. However, there's a gapless phase for G less than -0.55, which is rather mysterious. So there are some open questions. So now let me finally come to my conclusions. So the Majorana-Hubbard model in various lattices has rich phase diagrams. Majoranas like to pair up to form complex fermions for strong enough coupling, at least in the one-dimensional case or the square lattice case. And these break discrete symmetries. And supersymmetry can be realized in both 1 and 2 dimensions, either in the one-dimensional case or in the 2-dimensional square lattice case. Okay, so I'll stop there and take any questions.
Thank you.
Sorry. I have a question about the universality of this transition. So you were saying which universality it is?
Okay, so the one-dimensional case, yeah, the one of the transitions corresponded to tricriticalizing, as I hope I explained.
Yes.
And yeah, in the two-dimensional square lattice case, we're again predicting that there's a supersymmetric transition if T2 is 0. And this was actually studied earlier.
Yeah, so this would be the, I guess for CFTD people, we would call it the XYZ model, or
this model was studied previously and was known to have a supersymmetric transition. I think Joseph Pachenko, among other people, studied this model. But what's rather unique is this model now appears coming from Majorana fermions in this case.
I see, I see.
So good question.
Are there any more questions for Ian?
Hi. You mentioned that at the tricriticalizing point, the perturbation, the relevant perturbation doesn't spoil the supersymmetry.
Yes.
Could you explain that a bit more?
Okay. Unfortunately, I think that was studied earlier in some field theory context. I think by Carty actually. So I guess we can take this field theory and which I've written down here somewhere. Yeah, so we can take this field theory. I think we can. I must confess, I don't remember now exactly how this works, but I think one can show that the at the critical point, the only term that destroys the critical point or the tricriticalizing point actually preserves supersymmetry. So we expect supersymmetry to persist for larger positive G, but for negative G, we expect a spontaneously broken supersymmetry, which corresponds to the Ising phase. I think this was studied in some earlier papers. Yeah, maybe I could send you a reference for that.
Okay, thanks very much.
Yeah. Other questions?
There are no questions.
Sorry, can I ask a quick question about the 2D thing?
Yeah.
So you mentioned this U1, emergent U1, and you said the sorry. So you had a boson field, and what is the leading perturbation that breaks the U1 for the boson?
Okay, so the leading perturbation that breaks the U1 symmetry is written here, and this is a dimension 6, and we showed that it remains irrelevant. So this term has dimension 4, and this term has dimension 6. So it's maybe not too surprising that at the critical point, this term becomes relevant at the critical point, but this term remains irrelevant. So its dimension decreases, but using the epsilon expansion at least, but it remains irrelevant at the critical point.
Is this a critical point for the theory with a fermion coupled to a boson?
Well, you can rewrite it this way. I mean, you can rewrite this in terms of bosons, and that might be convenient because you get an order parameter which corresponds to a superfluid phase. So the order parameter would become, I guess, psi bar psi. So you could write a boson, the psi bar psi. That's sort of the order parameter, which is bosonic. So it's maybe convenient to make a transition to a boson. And at the critical point, we expect to have a Goldstone boson because we have this broken U1 symmetry.
And in that language, would you have something like a cubic anisotropy for that boson?
Good question. I don't remember offhand. Yeah, it could be. Yeah.
Okay, thanks.
Any more questions?
Okay, if there are no more questions, let's thank Ian again. But we didn't thank him the first time. We should thank Ian. I don't have I have David only to help me here with the applause. But Ian, should we take a
Let's
short?
take a little break, and yeah, it's 5 o'clock in Britain. I'll come back with my second seminar.
Great, and apologies again for butchering your name so many times.
No problem. It's
And-
name is actually Scottish. So.
I see. You see, I was calling you by the wrong name many times before, but there was nobody.
Yeah. Actually, both Ian and Affleck are both Scottish.
Great.
I've got Scottish ancestors.
Did we say 5 minutes or how long?
But yeah, well, at 5 o'clock, I'll come back. Okay, or
Okay.
9 o'clock in Vancouver time. Okay.
Pourquoi pas. Et là, on va là, à côté du pot.
On est à côté, là.
Tu peux aussi mettre ça et un
C'est
fauteuil.
gros, ça, c'est pas...
Hey, Costa,
Meuble bas, là, ça, c'est bon, on va pas commencer à le beau. Là, oui, éventuellement.
Costa. I can't mute him from here. I have to do it. Oh, are you a host? I don't think you're a host. Oh, here. Costa. I think I should have, I think there's a way to make you host. Three-dimensional.
Nope.
I think.
Hey, Costas.
I got my video turned off.
Yeah. Hey, do you want to start soon?
Yeah, we can start now if you like. Yep.
Start now. So, yeah, this is the second talk by Ian. And I think I finally got the name right.
Yeah.
Thanks a lot. Yeah, you can take it at your leisure.
Okay. So I'm going to talk about the generalization of the Haldane conjecture, which is this famous conjecture he made for SU2 spin chains, which helped to win him the Nobel Prize. So I want to talk about a generalization of this Haldane conjecture to SUN spin chains. And this is motivated by cold atom experiments, which are actually realizing these spin chains. So here's an outline of the talk. First of all, I'm going to give a review of the Haldane conjecture for SU2 chains. Then I'm going to talk about SU3 chains. Then I'll talk about SUN chains. And then talk about topological mass generation. So first of all, review of SU2 chains. So Haldane conjectured in 1983 that half-integer spin chains are gapless. And so this was based on a mapping for large S to the SO3 nonlinear sigma model with a topological term. So the spin Hamiltonian is simply nearest neighbor isotropic S.S terms. And these are the commutators of the spins, and the spins can have value S, so S squared is S times S plus 1 times the integer. In a large S, we can map onto a sigma model. So we take Sj to be minus 1 to the j S times phi plus L. So there's an alternating term and there's a non-alternating term. And the non-alternating term is actually the cross product of phi cross d phi dt in the sigma model. A here is a lattice spacing. So the Lagrangian of the sigma model can be written this way. So phi squared is 1. So we have a velocity, which is 2js. We have a coupling constant, which is 2 over s. Then we have this famous topological term, which is 2 pi s. So for theta 2 pi n, which is equivalent to theta being 0, the model is known to be massive. This was shown earlier by Zamolodchikov and Zamolodchikov. For theta equals pi, Haldane conjectured that the field theory is massless. This was eventually confirmed about 10 years later by Zamolodchikov and Zamolodchikov. So this was surprising to condensed matter theorists that the spin chains are massive for integer spin, because for spin a half case, it was known to be massless in 1931 by Beta. This was surprising to high energy theorists, that the sigma model is massless for theta equals pi. So this surprised both condensed matter physicists and high energy physicists. And this conjecture was confirmed numerically in experiments for spin 1/2, 1, 3/2, and 2. So the last term is topological. I'm going to imaginary time, it's imaginary. And with periodic boundary conditions, it's like I n theta. So the contribution is e to the I n theta to the partition function. So we see that if theta is 2 pi n, then this is equivalent to theta equals 0. There are integral models that are gapless for any s, which involve fine-tuning biquadratic, bicubic, etc. terms. But these turn out to be special points in the phase diagram. So the gapless field theory for theta equals pi is equivalent to the SU2 level 1 Vesumino-Witten sigma model, as I showed some time ago. The phase diagram for the sigma model is shown below. So for theta equals pi, there's a critical point here, which is the SU2 level 1 point. So the coupling is weak enough, we flow to this point. If the coupling is stronger, we flow away from this point. And this actually corresponds to a broken symmetry phase for half integer spin, which can be thought of for spin 1/2 as a Moudjum-Dargauche model. For other values of G, so if theta is 0, we just flow to strong coupling. And it turns out that if we move slightly away, we can actually, by having alternating couplings, we can actually move away from this point. And again, we go into a gap phase. So to be in the gapless phase, we have to have translation symmetry, and the coupling constant has to be weak enough. So now let me move on to SU3 chains. So this was first studied by Bekoff, and I studied it in a series of papers with Mila, Lashko, Kim, and Weimer. Weimer was my graduate student. Frederick Mila is a professor at EPFL in Lausanne. Lashko was his postdoc, and Kim was his graduate student. So the simplest SU3 model has the form for positive J, just H equals J, sum over lattice sites, S alpha beta J, S beta alpha J plus 1. Now alpha is 1, 2, or 3. Sum over alpha and beta is implied here. The matrices obey the SU3 commutation relations. So commutator of S alpha beta with S alpha prime beta prime is S alpha prime beta delta alpha beta prime minus S alpha beta prime delta alpha beta. Sorry, there's a typo here, should be alpha prime beta. For the symmetric rep with P boxes, there are P bosons in each lattice site, and the bosons have 3 different flavors, which we can label 1, 2, or 3. So we can represent the S alpha beta operators in terms of bosons as S alpha beta is B dagger beta B alpha. So normally S alpha beta is traceless, but we can ignore this because this doesn't actually change anything. So we can make this traceless by subtracting a delta beta alpha term, but I don't bother doing it. So for J positive, the classical ground state is different boson types on neighboring sites. This allows many possible classical ground states. So if we label the bosons A, B, and C, classical ground state can be ABC, ABC, or AB, AB, or many other possibilities. We can make ABC, ABC the classical ground state by adding a second neighbor term. So we add a J2 term, HI, I plus 2, where HIJ is S alpha beta I, S beta alpha J. So we actually don't think that adding the J2 term is necessary. It could get generated dynamically, but we add it for convenience. So I should stress, we don't expect this classical ground state to actually occur in one dimension due to Coleman's theorem. Breaking continuous symmetries doesn't occur in one dimension, but it's a useful starting point. So it's useful to perturb away from this broken symmetry phase, which is similar to what Haldane did. So P equals K. Exhibits power law to K, which is consistent with the 3 sublattice structure. So we can actually derive a flag manifold sigma model from the path integral by writing the state at site J as as so Bu dagger J are the boson operators, and then we have some factorial multiplying this, some scalar multiplying this, and for for the symmetric representation with p sites, we can represent the state on each site as this phi u j Bu dagger j to the power p. And so phi u is a complex 3-component unit vector. P label is the number of bosons on each site, corresponding to the number of boxes in the single row representation of SU3. So due to the 3 sublattice structure, we can introduce 3 orthogonal vectors phi a, one on each an equivalent lattice site. And the imaginary time Lagrangian can be written as follows, which we can extract from the path integral by assuming that we're close to being in the broken symmetry phase. So Lagrangian actually has 3 orthogonal unit vectors, phi n, and is 1, 2, or 3. And there's a topological term. And there's also another strange term which is imaginary, but which is not topological. So these three phi n vectors are basically 3 CP2 vectors, which are orthogonal to each other. And that's what we can derive from the path integral. And the velocity is 3 AP square root of J1, J2. Coupling constant 1 over G is P times root J1, J2 over J1 plus J2. So we see that as P gets larger, coupling constant gets smaller. And the topological terms can be calculated. It turns out that theta 1 is minus theta 3 is P times 2 pi over 3, and theta 2 is 0. And this other additional strange term lambda has the value 2 pi over 3, 2J1 minus J1 over J1 plus J2. So theta n and lambda are imaginary terms, but the lambda term is not topological. So the 3 phi n vectors are orthogonal to each other. This is basically 3 CP2 models with orthogonal vectors. And this is equivalent to a flag manifold signal SU3 over U1 cross U1. So we conjecture that the model is gapped for P a multiple of 3, corresponding to the theta angles being 0, and is gapless for other values of P, and then it maps to the SU3 level 1 Vesemina-Witten model. So by the way, we can see that the third topological angle can be made 0 because phi 3 star can be written as phi 1 cross phi 2. And it's possible to show that the topological term for phi 3 can be written as simply minus the 2 topological terms for phi 1 and phi 2. So that tells us that the sum of the topological terms actually adds up to 0. So we only need to keep 2 of the topological terms. Convenient to only keep theta 1 and theta 3. And starting from the path integral, we can prove that theta 1 is minus theta 3 is P times 2 pi over 3. So if P is a multiple of 3, topological angle is effectively 0, but otherwise P is non-zero. So we can check that a gapless phase may occur if P is not 3n using the Lieb-Schultz-Mattis Affleck theorem. So we consider the unitary operator U, which is exponential of I 2 pi over 3 sum over all sites j times qj, where qj is S11 plus S22 minus 2S33, which can be written as P minus 3 B dagger 3 B3. These are the boson operators. So qj is a generator of SU3. Now, if we consider the operator U dagger HU, this can be written as H plus I pi over 3 commutator of H with this term plus order 1 over L. Now, if we calculate psi U dagger HU psi minus psi HU, this is order 1 over L because it's of translation symmetry by one site on U. So this term can be actually dropped. So we get terms of order 1 over L. So T inverse, if we did translate by one site, T inverse UT translates into e to the I 3 pi over L J sum over J Qj plus 1. It translates Q to J to Qj plus 1. Using periodic boundary conditions, QL plus 1 equals Q1. So we can write this as e to the I 2 pi over 3 sum over Qj plus 1 from 1 to L times e to the I 3 pi over L Q1. Now, if we use SU3 invariance of the ground state, this implies that the sum of Qj plus 1 psi is 0. So therefore, this exponential operating inside us gives psi. E to the I 2 pi 3 pi over L times Q1 gives e to the I 2 pi over 3p times e to the I minus I 2 pi over 3 b dagger 3 b3. And this just gives 1. So this tells us that we get a phase of e to the I 2 pi over 3 p times the identity matrix. So the effective translation by one site is to give us this this phase. So if yep.
So did you use the full SU3 invariance or just the U1 subgroup?
We use the full SU3 invariance, but just we're just using a U1 subgroup, I guess, for this calculation. Yep.
But does that mean that so could you break the SU3 symmetry down to something smaller and still have non-trivial conclusion? I think it should be.
Yeah. So I guess this operator actually breaks the U1 symmetry down, U3 symmetry, SU3 symmetry down by operating with this operator. So I guess it breaks it to a subgroup. Yeah, yeah, good question. Maybe a U1 subgroup.
Right. So I think the conclusions of the theorem are actually stronger, right? You don't need a full SU3.
Yeah, that's right. Yeah. Okay. So now if we calculate psi, so we translate by one site, we can assume that psi is we have a phase. So under translation by one site, we pick up this phase. So if P is not 3n, we get a non-trivial phase here. So this tells us that the state psi is orthogonal to the state U psi. So U psi is a low energy state which is orthogonal to psi for P not equal to 3n. It can also be shown that if we translate by two sites, we pick up this phase e to the I 4 pi over 3 times P. So translation by two sites also gives us a low energy orthogonal state for P not equal to 3n. So this actually leaves two possibilities. Either there are low energy excited states for P not equal to 3n, or else there is a broken translation symmetry. So for P equals 1, we can find the analog of the Majumdar-Gauche broken symmetry states. So we can combine. So if we have P equals 1, we can combine three sites to form a singlet. And we have three different ways of doing it. So it's the analog of Majumdar-Gauche, but we have three different states. So we can combine three states to form a triplet, a singlet, either these three, or these three. So we're forming singlets from three neighboring spins. There's three ways of doing it. On the other hand, for P equals 3, we can form the analog of the AKLT state. These states were presented by Greiter, Rachel, and Schuricht. So now we have three states because P equals 3. And we can combine, again, three states to form a singlet. But now we actually have translation invariance. So we can see that if we take, for example, this site, we have a triplet going to the right, a triplet going to the left, and a triplet which has one term in the left, one term in the right. And we can see that the same thing happens on the next site. Again, here we have a triplet going to the left, a triplet going to the right, and a state which is has a state on the left and the right. So this is translation invariant. So for P equals 3, we can form the analog of the AKLT state, which is translation invariant, and we expect it to be gapped. But for P equals 1, this is a possible broken symmetry state, but we also expect to get non-broken symmetry states. And we find with a correction that was made by Amori, Seiberg, and Schaap, normalize large values at small energies. Nevertheless, for P not equal to 3n, the model is gapless, we're normalizing to SU3 level 1. But for p equals 3n, it's gapped. And this was shown by Amori, Seiberg, and Shao. This is consistent with the 't Hooft anomaly. I should mention the 't Hooft anomaly was first applied to these field theories by Tin and Tanizaki. So it's confirmed by the beta ansatz for p equals 1. We confirmed it numerically by Gozel, Nataf, and Mila for p equals 3, that there's a gap for p equals 3, and p equals 1 is known to be gapless and correspond to SU3 level 1 from the beta ansatz. So in our original paper on the topic by Lajko, Weimer, Mila, and Affleck, we studied the sigma model numerically, including the topological terms, but not the lambda term, and we confirmed the expected behavior. So we found that when the topological angle was 0, we had a gap, but when the topological angles were 2 pi over 3 and minus 2 pi over 3, the model was gapless. However, we didn't include the lambda term.
So, question?
Yep.
Can you say a little more about this 't Hooft anomaly argument?
I think the 't Hooft anomaly is somewhat reminiscent of the Lipschitz-Mattis-Affleck theorem, except it applies to the field theory. And I think it tells us that certain states can have broken symmetries and other states cannot.
I see, but what symmetry are you applying this to? Is it SU3 or?
I think it's
translation.
So for the field theory, I think it's there's a discrete Z3 symmetry which corresponds to translation.
I see.
Which I think maps the 3 sigma models into each other, the 3 CP2 models into each other.
Thank you.
Yep. So this is our conjectured phase diagram. So it's reminiscent of what we had for the SU2 case. So now if theta is 2 pi over 3 or 4 pi over 3, which are equivalent, then we have an SU3 level 1 critical point. So if the coupling is weak enough, we flow to this critical point. However, if the coupling is strong enough, we go into this broken symmetry phase, which I illustrated. If theta is not 2 pi over 3, we just flow to strong coupling. And so for theta is 0 or 2 pi, for example, we just flow to this unbroken symmetry, strong coupling phase, which we can think of as being the analog of the AKLT state. And for theta equals pi, we also expect a gap phase. But for small enough g and theta 2 pi over 3 or 4 pi over 3, we're predicting this SU3 level 1 critical point. So we also studied self-conjugate representations of SU3 with one row of length 2p, one row of length p. We again studied the same flag manifold sigma model, but now we had 2 different velocities, so this destroys Lorentz invariance. The topological angles are now plus or minus p times pi. So we conjecture that the models are gapless for all p, are gap for all p, I mean, but have spontaneous broken translation symmetry for p odd. We can find AKLT states that support this. Following Mathur and Sen, we can write S alpha beta in terms of 2 bosons, S A dagger alpha A beta minus B dagger beta B alpha, with B bosons and PA bosons in every site. So for P even, we can write a translationally invariant AKLT state. So this is the state. So we have, we can form, so these are 2 neighboring sites. So we take alpha 1 to alpha p over 2 and beta 1 to beta p over 2 at this site. Then in the next site, we have beta 1 to beta p over 2. So these are matched, and the lower index corresponds to A and B bosons. So here we have alpha, here we have beta p over 2 plus 1 to beta p, and here we have beta p over 2 plus 1 to beta p. So we have basically the same thing on every site. So we have the analog of an AKLT state. For p odd, there are 2 corresponding states with broken translation symmetry. So this is for p odd. So now we have beta 1 up to beta p plus 1 over 2. And then we have beta 1 to beta p plus 1 over 2. But now we have beta p plus 3 over 2 up to beta p and beta p plus 3 over 2 up to beta p. Or we can do beta 1 to beta p minus 1 and beta p plus 1 to beta p. So now we have two different states which break translation symmetry because these are inequivalent. So here we have p plus 1 over 2 of these states, and here we have p minus 1 over 2 states. So we break translation symmetry. So we have an AKLT state for p even, but we have two different states which break translation symmetry for p odd.
Could I interject with a question?
Yep.
So, can you actually find a model for which the AKLT state is a genuine ground state for some?
That's a good question. I think, I think that might have been. I think Greiter, Rachel, and Strick might have found states that did this. I think if you consider, if you sort of fine tune biquadratic and bicubic states, I think yes, you can find states that will give you the AKLT state as a ground state. Yeah, good question. Similar to what we did for the SU2 case.
But you also said that there is a beta-hazard solution for these.
Only for p equals 1. Yeah.
Only for p equals 1, not
Yes.
for.
Yeah.
Or 2 or higher. So for p equals 1 of any SUN chain.
Yeah, any SUN p equals 1, you can show that for nearest neighbor interactions, it normalizes to the SUN level 1 Bessamino-Witten model.
Okay, thank you.
Yep. So for other representations of SU3, using flavor wave theory, we find a combination of a quadratic and linear dispersion. So it's a so-called fairy magnetism. So we have partially ferromagnetic and partially anti-ferromagnetic. So some combination of ferro and anti-ferromagnetism. So ferromagnetism can exist in one dimension, but anti-ferromagnetism cannot exist in one dimension. So we haven't studied these models carefully. So there's some interesting open questions here about what happens in these more general SU3 models, and do we get some sort of combination of ferromagnetism and Haldane gap type states, which we haven't tried to study. So now I want to discuss generalization to SUN. So generalization to SUN was again first presented by Bikoff in a special case where the velocities are equal in the field theory. So Wehmer, Lashko, Milo, and I extended this to arbitrary SUN models in the symmetric rep. So classically, the local zero modes occur unless there are any ferromagnetic interactions up to n-1 sites, which we included. So although the bare velocities are all different in this case, we showed that they were normalized to become equal. So therefore, even though we can have different velocities in the lattice model, we predict that they were normalized to become equal in the field theory. And the n-1 topological angles take the values 2 pi p over n. So inspired by results of Omori, we conjecture the model is gapped with no broken symmetry if p is an integer multiple of n. And it flows to the gapless SUN level 1 model if p and n have no common integer denominator. And they're in a gapped broken symmetry phase if p and n have a common integer denominator. And the degeneracy of the ground state is given by n over the greatest common denominator of p and n. And related work was done by Tin and Tanizaki. So we showed that the only representations of SUN for n even, which have linear dispersion, correspond to 2 rows of different length. More generally, we get a mixture of linear and quadratic dispersion called ferromagnetism. We expect that ferromagnetic order may exist even in one dimension, but again, the anti-ferromagnetic order cannot exist. So now I want to talk about mirons. So for the SU2 case, long ago, I wrote a paper arguing that we can think of the mass gap as being produced by mirons. So mirons are basically half instantons. So this was based on reducing the symmetry to U1 by introducing a mass term. So for SU2 and the SO3 representation, we simply add a m phi 3 squared term for positive m. So this produces the familiar U1 model, which produces a mass gap from vortex proliferation. So at the cores of vortices go to the north or south pole to avoid an ultraviolet divergence. So we have two types of mirons. So at infinity, the bosons lie on the equator, but at the origin, they go to the north or south pole. So we have two different types of mirrons in this case. So we can also do this in the SU2 notation, so CP1 notation. So in this case, we can write phi as 1 over root 2, 1 e to the I omega. So at the origin, phi goes to either 1, 0 or 0 e to the I omega, which corresponds in SO3 notation to going to the north or south pole. So the phase omega in the second term can be eliminated by a gauge transformation. So it doesn't produce an ultraviolet singularity. So there's an infrared logarithmic divergence, which is familiar in the Sine-Gordon model. Vortex-anti-vortex pairs have a logarithmic dependence on their separation. So these are half instantons. So if the topological angle is 0, the two mirrons give the same positive contribution. But if the topological angle is pi, the two inequivalent mirrons contribute e to the I pi over 2 plus e to the minus I pi over 2, which is 0. So thus mass generation doesn't take place, and we can extrapolate m to 0. So this was the argument I gave long ago for a gapless phase for theta of pi, and a gap phase of theta is 0. We can generalize this to SUN for the symmetric reps with p boxes. Now we have the following two terms to the Lagrangian. So we add a term, so alpha and beta run over 1 to n. So these are on-site terms. So we can have a m phi alpha beta squared, absolute value squared, minus phi alpha gamma squared, where alpha goes from 1 to n and beta is less than gamma. And we have an additional term, which is phi 1 alpha beta star to the n minus Hermitian conjugate phi 1 alpha star phi alpha beta to the n, and this whole thing is squared. This reduces the n vector field to a single U1 while preserving the Zn symmetry. So the first term is minimized by choosing phi alpha beta to be e to the I over e to the I sigma beta. And the second term becomes 4mn sum over beta sine squared of n sigma 1 minus sigma beta. So by a gauge choice, we can set sigma beta to 0. That leaves only the sigma n as the free variables. And so we get the analog of the SU2 term, U1 term, but now we can divide the topological charge for each of the n fields into a contribution from infinity, the contribution from the origin. So infinity, the nth topological nth component of each vortex becomes 1 over root n e to the I omega, which contributes 1 over n to the topological charge for each vector. At the origin, one of the vectors goes to 0, 0, dash, 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 e to the I omega transpose. This contributes minus 1 to the topological charge for that field. Thus, the total contribution to the topological charge in the action is sum over k e to the I 2 pi pk n over n. So as long as p is not a multiple of n, this sum vanishes. So at first glance, this seems to rule out massive phases when p and n have a common denominator with a winding number j. We obtain a contribution sum over k e to the I p kj over n. This will make a non-vanishing sum if n over p is an integer, which we can choose to be j. So we can conclude that larger vortices or larger instantons will still make a contribution, and this is consistent with this contribution. So actually, I'm finishing this way early. This is only taking about half an hour, but here are my conclusions. So we've extended the Haldane conjecture to SUN. We've mainly studied single row symmetric reps. We also studied self-conjugate SU3 reps. We also studied SUN with 2 rows of different length. So many reps contain linear plus quadratic dispersion, which we think exhibit ferromagnetic behavior coupled with some sort of Haldane behavior. This needs further study. Okay, so that's it for the talk, and I apologize for only being half an hour. So any questions?
That's quite all right. Thank you for the questions.
Yeah, you mentioned in the beginning cold atom experiments.
Yeah.
Could you say a little more? How does one?
Yeah, I think that so certain okay, I think certain atoms, the nuclei can be in basically SUN states, so that they can be in symmetric states that have several different states for the ions, the nuclei, and they can have an SUN symmetry. So there have been some experiments which have tried to produce these cold atom states. So I think SU3 is possible, and maybe SU4, maybe even SU5.
I see. Do you know where these experiments are?
There's actually a little conference in these experiments I went to in Japan a few years ago. I think that people have done these experiments maybe in the United States and maybe France and Japan, maybe other countries.
Okay, thanks.
Yep.
Other questions?
Hi. So in the SU2 case, the extra degree of freedom in the matrix in the WCW model compared to the sigma model you can think of as the dimerization, is that also true for the higher end?
Yeah, so the diagram is very similar. This is a diagram that I actually worked out years ago for SU2. So this is Bajun-Ragosh over here, broken symmetry for half integer spin. For small enough g, we go into the SU2 level 1 phase. If we have alternating couplings, so they're not equal in every site, we move away from this point. We can show it changes theta away from pi. So we get a gap phase. So the gap phases are only, gapless phase is only stable if the coupling is weak enough and we have translation invariance. And the phase diagram for SU3 was quite similar. So again, for theta of 2 pi over 3, we have it, and for small enough g, we have a gapless phase. We float to SU3 level 1. But for stronger coupling or moving away, or either theta equals 0 or 2 pi, or moving away by breaking translation invariance, we go into a gap phase. So the gapless phase only exists if we have translation invariance and we have small enough coupling, and theta is 2 pi over 3 or 4 pi over 3. So this is a prediction about the field theory. In this case, the flag manifold sigma model.
Thanks. But
Yep.
can you heuristically, can you identify the degrees of freedom in the matrix of the WCW model with the fields of the flag sigma model plus some additional fields which represent dimerization?
I think even in the SU2 case, this is kind of non-trivial. So we're sort of going from the O3 sigma model to the Vesamino-Witten model. So there's not an obvious connection of these two models. So the O3 model has 2 components. The Vesamino-Witten model is an so I think it's not obvious. I mean, I think it's a very non-trivial mapping. It basically takes us from the O3 model to the SU2 level 1 model. So I think there's not an obvious mapping.
May I make so there was a section in my paper with Yuya where we deformed the Vesamino. We were basically trying to reproduce what you do with the SU2 Vesamino-Witten model.
Yep.
You deform it to reduce the symmetries down to the symmetries of the sigma model.
Yeah.
You get the theta term and you get the sigma model. We did something similar, and we even got the lambda term that you have, some specific one, when you reduce the symmetries of the SUN Vesamino-Witten model.
Okay. Yeah. Yeah.
So that gives you kind of an idea of what these degrees of freedom
Okay.
are.
Yeah. Sorry, I can't see your name here. I'm curious. You wrote a paper?
Thin.
Okay. Yeah. So you were involved in some of these papers?
So Tin and Tanizaki. Tin
Okay. Yeah. Okay. Yeah. Yeah.
And my name is not written correctly because I'm in the room.
Oh, I'm sorry. Okay.
in that paper that we wrote, there's a section about that. It's been a
Okay.
while. I can't remember the details.
Okay. Other questions?
Actually, could you elaborate? I think I got lost in this when you were trying to argue similarly, like for SU2 case. In SU or O3 nonlinear sigma model, you break down the symmetry down to U1.
Yeah.
And then you have vortices, which, you know, if the coupling is small enough of this U1 nonlinear sigma model, then the vortices will percolate and gap the system. But in this, I didn't fully understand. Are you breaking this flag sigma model?
Yeah, we're breaking the symmetry. So in the SU2 case, we break the symmetry down to U1, and we're doing something similar in the flag manifold sigma model. We break it to U1.
So it's a single scalar, compact scalar.
Yeah, so we just have these vortices, very similar vortices to like happens in Kosterlitz Thalys.
I see.
Which were shown to produce a mass gap for the, I guess the Sine-Gordon model.
I mean, one of the nice things was in the SO3 case or O3 model was that when theta is equal to pi, all these vortices vanish, and that the same thing you get. I mean, you don't get the contribution of the leading vortex, only the.
Yeah, we found something similar, but more complicated for SUN. So basically, for certain values of the topological term, there's a cancellation of these vortices.
Mm-hmm.
But it's a bit more complicated to explain. I've got a paper on this with Kyle Waymer, which you might like to read if you're interested.
Okay, thank you.
Yep. Other questions?
Is there also, are you forced to break it down to one U1, or could you?
Yeah, we break it to a single U1, which happens from these two couplings. Yeah.
Is that the only choice, or could you have multiple U1s?
Well, I think if you want to have the standard vortices like in the Kosterlitz Thalys model, you want to have a single U1, which we've chosen to do here. There might be more interesting ways of doing things, but this is what we studied in my paper with Kyle Waymer.
Okay, thank you.
Yep. Other questions?
If not, let's thank Ian again. And thank you again, Ian, for.
You're very welcome. Yeah.
Especially since it's early
yeah.
webinar. And I think tomorrow we have a discussion session with you and she.
Okay.
Because you're both on West Coast, so.
Yeah. Yeah. Okay, I'll be there. Yep.
Fantastic. Thank you so much, and
okay.
have a good day.
You too. Thank you. Bye. Good evening.